we're talking about, we're introducing this idea of generative adversarial networks, which was first introduced by Ian Goodfellow, and who also other people in this field characterized as one of the most innovative ideas in the last 2 years with regards to machine learning. And as the name suggests, it uses deep learning to generate data and is trained along an adversary, another neural network, as we will see. So the main thing to see here is the impact that this had on the community. So around the time that it started to, it was published around 2016, you see that only a few papers referred to the term GANs and adversarial networks. And after that, you can see that the amount of people interested in working on this idea has increased dramatically over the years. So that gives you another idea of how revolutionary or groundbreaking was at the time. So the main idea in GANs is that we just want to generate new samples that are similar to the data that we have, our original data, without having to model the underlying distribution or worry about the distribution that generates this data. But this complicates things, as we may have a complex distribution to learn from the data, which might be difficult to learn in a generative model. So GANs try to mitigate this problem by having a generator network that starts from random noise to generate a new image. And is trained to learn the transformation from a random noise to the distribution of the data. And the main objective here is that we want the generated samples to be as close as possible to the real data. And the main breakthrough to achieve this in this GAN structure, where we have two neural networks, one called the generator and one called the discriminator. And these two are competing against each other. Specifically, the goal of the generator is to go from this noise to produce imitations of the data that are close as possible to the real data. Then the job of the discriminator network is to take this, both the fake data generated by the generator and the real data, and learn to distinguish between the two. So by having these two networks compete against each other, we can force the discriminator to become as good as possible at distinguishing between real and fake images. And at the same time, as the discriminator becomes better and better, the generator becomes better at generating images that can fool the discriminator. And we will see that this is a really powerful idea. So, but first, let's consider a more intuitive example on why this process actually works. So let's say that we want to generate faces. The generator will start from some noise. We'll start producing some samples representing here in this 1D line. And that will not be that good in the beginning. So it's going to be really easy for the discriminator, once it sees what is real, the real images as well, the fake, to discriminate between the fake and the real images. So once the discriminator is training, it tries to predict what is real and what is fake. So the discriminator outputs some probabilities on whether each of these data points is actually a true or fake. And as we'll train the discriminator, it's going to get, maybe at the beginnings, it's a bit, cannot tell what is real and what is fake, but over time, its prediction will become better, and it will assign a higher value to the real images and a lower value to the fake images. Until we get this perfect separation where the discriminator now is quite confident on what is fake and what is real. So in response to this, if we do this process over and over, the generator sees where the true data points lie. So in response, it's going to try and shift those points into the area that the real data belong to. Then these new points go back to the discriminator that then adjusts the probabilities again of each point, if depending on if they are real or not. And it will again try and predict a high number for the real and a low number for the fake samples. And it continues to adjust. And this cycle will repeat itself, and the generator will start to see more and more where the space of the real samples are, and will try to move its prediction towards that space, closer and closer to the real data. So the goal is to eventually make it really hard for the discriminator to distinguish between fake and real data points, while the generator will continue to generate fake data points. And over time, you will see that the generator will start predicting more and more realistic faces. And this is the main core intuition behind how GANs work. So you can see how these two networks are adversaries of each other. They compete to fool one another. What we can do after this training is is to use the generator to sample new data points and create new data that we have never seen before. Now let's start to move now into how we can formulate this a bit more rigorously, so we can train two neural networks to train through the GAN structure. So as we said, we have this generator that generate fake samples from a random vector z. So we call this process g of z. And then we have a discriminator that tries to distinguish between the real and the fake samples. And we have basically this d of x, which is the probability for a real sample. And it should start close to 1. So at the beginning, the discriminator is highly confident of what is real. But over time, what G tries to do is to push that toward 0.5. And then at the same time, it tries to make its own predictions and push the predictions of the discriminator when it's given a fake sample, the G of Z, to go higher as possible. So converge again to some value around 0.5, where the discriminator cannot distinguish between real and fake. That's the main idea. And we train these two against each other to get a better generator and a better discriminator. Now, the overall objective function of GANs is shown here. It's basically a measure, in a high level, it's a measure of how well the discriminator does in discriminating between the fake and the real samples. So the discriminator here gains maximum reward if it correctly classifies the fake from the real. And the generator tries to minimize the value that the discriminator can achieve. So it's a min-max gain. That's how it's called. And so we basically here take this expected value that this discriminator can achieve over the real data and the fake data, which are provided by the generator. And in that way, the generator tries to implicitly minimize the reward that the discriminator can achieve. So in this, thinking about this in terms of training neural networks, we basically have two separate networks. And the training algorithm has to, at the same time, address two complications. First, we must juggle between two different kinds of training, the generator and the discriminator. And so this causes convergence to be hard to identify. And the generator and the discriminator have different objectives and training processes. So how can we train them together as a whole? So for this, we can define two separate loss functions that basically are components of the original objective in the min-max game, and then use them to train the two neural networks. So in game theoretical terms, this GAN is based on a zero-sum game, where in short it means that if one wins, the other loses. And each player tries to maximize their own actions and minimize the actions of their opponents. The optimal solution to this is called the Nash equilibrium, and it's achieved when none of the two want to change their actions anymore. So this equilibrium is achieved where no one wants to move from the position they are. So in GANs, this is achieved when the generator matches the true distribution of the data, and so it has as a result that the discriminator cannot distinguish between the real and the fake data. And we usually tackle this in a heuristic way, so in a multi-step way. So first we fix the generator and perform the gradient step to update the discriminator, and then we fix that discriminator to update the generator, and we keep repeating these two steps so as to achieve in order to achieve the optimal objective. Now, in terms of the data flow here, we have of the training process, we have the generator output that is connected to the directly to the discriminator, and through backpropagation we can update both the discriminator and the generator. And let's explain a bit in more detail this process. So the discriminator here is again a classification network, as we've seen in previous lectures. So it tries to distinguish between the real data and the data created by the generator. So the training data for the discriminator comes from two instances. It comes from the real images, and then it also comes from the generator. And we can label these two because we know beforehand what is real and what is not. We have a label for each of these images. And then we pass that through the discriminator. And basically, the discriminator loss is a binary cross entropy that for each of the instances, and it's how well the discriminator did in predicting the true value of each of the images. Then we can apply backpropagation just for the discriminator part, using the output of the generator and the real images. And this is the way we train the discriminator. Now, the generator part learns to create fake data by incorporating feedback from the discriminator. Remember, in the loss function, g of z does not appear on its own, but it appears within d. So we have the d of g of z. This implies that we need some feedback from the discriminator to train the generator. So it wants to learn to make the discriminator classify its output as real. In this basic form, we take a random input, we pass it through the generator to generate the sample. And then we pass the sample, the image generated from the generator through the discriminator. And basically, we want the discriminator to have a misclassification. And then we backpropagate from that loss to through the generator. However, we do not update the weights of the discriminator. We just compute the gradients up to that point, and then we flow those gradients back to the generator to update only the weights of the generator. So in this way, we achieve to train the generator by having feedback from the discriminator, so we can then so the generator learns over time how to fool the discriminator. Now, a bit more details about the generator and discriminator. So both of them are deep convolutional neural networks. And the generator in particular converts this Z vector, this random vector, into an image that has to have the same size as our target, and it has 3 channels, so an RGB image. So in practice, we do this by passing into a series of transpose convolutions, as in the same way as we had with the segmentation networks. And it has been shown experimentally that using patch normalization helps after each layer. For the activation functions, people normally use the ReLUs for the inside of the inner layers of the generator, and for the output they use a hyperbolic tangent that keeps the range of the values between 0 and 1, -1 and 1, sorry. And then converting those values into RGB values is rather straightforward with a simple transformation. Now, with regards to the discriminator, again, the discriminator is rather a simpler deep learning model because it's just like any other classification network, binary classification network. It takes one image and outputs a scalar. That's the probability that the image is real or fake. So basically, in this architecture, it's again composed of a series of convolutions, patch normalizations, and leaky ReLUs. And the output is a sigmoid function to say if it's a real or fake image. So typically, again, here, people also use strided convolutions rather than pooling. Again, patch normalization and leaky ReLUs are used to promote the flow of the gradients because now this discriminator is used as an additional component on top of the generator. It's important to maintain good gradient flow through the generator so that it can reach the layers of the discriminator, so it can reach the layers of the generator. So overall, the goal of GAN training is to reach this Nash equilibrium where the discriminator effectively does no better than a random chance. So the probability of selecting a fake or real, classifying a fake or real, is 0.5. However, this is a difficult training process in general, and there's no guarantee that it will reach that equilibrium. So there's a number of things that can go wrong during training in a GAN structure. So the discriminator feedback, as it tends more and more towards a random chance, it gets really less useful for the generator to use over time. So this could pose a problem. And it could provide mixed signals to the generator and break all the training. So yeah, overall GANs are difficult to train, and there's a lot of tuning that has to go when training GAN structures. So we have some common problems, as I alluded to. The vanishing gradients problem is still can appear in GAN structures. So if our discriminator, especially in the beginning, if it's too good to discriminate between real and fake, then the generator will basically get no loss function, no loss signal. So the gradients will be really small. And there have been some attempts to remedy this through various training strategies. So you could have different learning rates for the generator and the discriminator, or you can use some other loss functions that try to address this particular problem. So finally, one of the problems I would like to emphasize on is this idea called this problem called mode collapse. So mode collapse refers to this phenomenon where we have the generator that finds small subsets of the examples that can't fool the discriminator and only output those values because they do the job. During the training, the loss function is minimized using just these examples. So the variety in the outputs of the generator is not so high. Now, if the discriminator learns to do well on those outputs, the generator just shifts to another subset of the data, and it does not keep learning different various forms of data. So if you see in the image, in the output, so it keeps moving around different subsets of the data space rather than actually learn to generate all the previous subsets as once. And this is called mode collapse. So for example, it could stick to generating one particular type of face if we're interested in face generation. Then once the discriminator gets better, it could shift to something else, but it will not keep producing all various different types of faces. And this is, again, a problem that we can tackle with, for example, again, playing around with different strategies for learning by changing the learning rates. Or we could try and get some statistics from the real batches and the fake batches and try to make them match. Or one other thing is that we keep some of the previously generated samples to give the discriminator so it doesn't forget what the generator generated before. So the generator now it would be forced to find some to keep learning those as well. So let's focus now a bit more on specific architectures and some results. And we will see some different approaches that build on this basic GAN formulation. So starting from a simple DC GAN, that is basically what we just described, you can see here some results. So in the yellow boxes, you have the real images. And on their adjacent column, it's the nearest neighbor from the generated samples. And you can see here that these nearest neighbors are not identical to those images, which means that the generator has not learned to mimic the data, but it rather produced something that is close. Okay, and this is important. We don't want the generator to memorize the data set. We want it to generate something that's completely new. So similarly with this idea of entangled variables that we saw in the variational autoencoders, we can also find some interesting structures in the latent representation stemming from the random noise vector. So for example, here, if we have some vectors that generate images of men with glasses, and we have some other vectors that generate images of men, and then we have some other vectors that generate images of women. If we subtract the vector that generates men from the vector that generates men with glasses, and we add the vector that generates women, we get up a vector that will generate women with glasses. So you can start to find really intriguing properties in these latent spaces. And this shows you that there is some structure that is encoded in these noise vectors that the generator has learned to transform into some meaningful representation of our data. Now, the problem with this is that this is not a systematic procedure. So it's a very manual procedure. You need to generate a bunch of images, find images that have the characteristic you want, and then go back to get those vectors and average them together to capture some structure of interest. So it's a really manual process. So at this point, it's still not clear how to change the input to the generator to get a meaningful change in the generated examples with some structure. And this, for this reason, InfoGAN was proposed. This is an information theoretic extension of the GAN framework. So the main idea is that it's able to learn disentangled representations as we had with variational autoencoders. And it does this using a latent code that we denote with C. Now, this C value, this C code, is concatenated with that Z vector, and that is what goes into the generator. So we have, it basically acts an extension to the noise vector. And the idea is that different variables can correspond to different attributes through the encoding of that C vector. So if we have a data set of faces, a useful disentanglement will be to have one attribute, one variable that will correspond to the expression, one to the eyes, hairstyle, and so on. And the idea of this code is that they are made meaningful because we try to maximize the mutual information between the code and the generated output. And here basically is the loss function. So they add this term that is the mutual information. So how correlated are the code with the generated output. And it introduces some similar ideas to the variational autoencoder. So if you map this code into a prior distribution, then you can see that it will get some structure. Then the structure will be used to train the generator, and this is controlled. There's also a controlled parameter lambda that you can increase or decrease to make the representations of the variables entangled or disentangled. So that is done to disentangle the variables in the vector, but sometimes it's also useful to Okay, so the connection went a bit down. Can you hear me?
Yeah.
Oh, yeah, it's fine.
Okay. So as I was saying, InfoGAN was more focused on disentangling the variables. Sometimes it's useful to train a network to generate some samples conditionally. So that can be based on some of the class or some type or some other condition that we set. And this is done with a simple modification to the original GAN framework that basically we condition the model on this class label or type that we want. So the generator now will be a function of some other input other than the random vector z, and so will the discriminator. And we feed this information to both. And this, of course, is needs to be, we need to have explicit supervision signals if we are to do this. So we need to have some form of labels or something else. So, for example, in this conditional GAN case, where we want to generate digits, we can have the one-hot encoded vector, which is the class of the label, and we input this to both the generator and the discriminator. And so it will learn to generate specific digits based on this vector. So another interesting idea that we've seen in the last 2 years is this example of work by NVIDIA called progressive growing of GANs. It's basically this idea is to train a GAN in an iterative fashion by increasing its the resolution of the images involved, but also increasing its number of layers progressively. So as training progresses, we keep adding more and more layers and increase the spatial resolution of the output image. This is good as it allows the network to learn to generate the right amount of detail at each iteration, and it learns to add features more gradually. So it can basically move into higher resolutions much smoother than training it from scratch. And it generates outputs that are quite realistic, as you see in the images in the example here. And these images are all examples of fake celebrities. So these are images of people that do not actually exist. Another form of GAN is this cycle GAN, which is another idea that is a bit different. The idea here is not to generate an image, but rather to transfer features or a style from one image to another. So in this example here, for example, we are transferring these zebra features into images of horse, and we get the image on the video on the right. The interesting thing here is that it did not only learn to change the features, but it also learned to change some of the background to meet the target domain. So this means that probably zebras live in a different type of class of grass than horses. And a similar approach can be used also for audio signals to transfer the voice of one person to another. So the main idea in CycleGAN is that the process of this transferring can work in both ways. So it introduces this form of cycle consistency term to the loss. And the idea is that if we go from a domain X to domain Y, so from zebras to horses, we can then use go back from zebras to horses. And for this reason, this framework uses 2 generators and 2 discriminators, one for each direction. And if we transform, for example, a horse to a zebra and back again, the result should be close to the original image. And this cycle consistency loss is a combination of the loss of the both discriminators together. And the idea is that both of them will not be able to tell the difference between the generated images. Another application that you may have seen an app for it is this idea of face aging, which again uses conditional GANs. So the generation here is conditioned on a discrete one-hot encoded embedding of age categories. And it first uses an encoder to learn the inverse mapping of an input face into some latent representations. And it uses here 2 different types of losses. So we have this pixel-wise loss and this identity preserving loss. So it lets to generate images with these 2 losses. And then by getting the encoding from the identity preserving latent variable and use it together with the age encoding, we can get an image that looks the same as the original image, but is aged by the age that is encoded in the code. We also have this image-to-image or pix-to-pix models. So this is a more generalized idea that we can take one image and transform it into a different domain. And they call this approach image-to-image translation. And it has a lot of different tasks, like, for example, going from a segmentation image into a realistic image, or from a drawing to a realistic image. And the idea here is that the discriminator is provided with both the source image and the target image, and it must determine if the target that is generated is plausible with respect to the source image. So it's a form again of a kind of conditional discriminator. Also, we can have different types of data to be used in a GAN framework. So it's a general enough framework that we can put different types of codes in along with the random vector. So for example, here we can encode some text using maybe another type of deep learning method that is more appropriate for text. And we create an embedding for that, so some representation. We can concatenate that with some random vector, and what we get to the output is not only a generated image, but also some text that describes this image. And again, if we do this, the generation process is conditioned on the text. So we basically type some text of what image we want to generate, and the network learns to generate the image that corresponds to the text. And in this case, we have different types of what are fake and real. So we can have, so for the real, we have the real images along with the real text description. But for fake images, we can have real image with wrong text and fake images with some form of right text. So we have many more combinations. Finally, I would also like to talk a bit about the concept of deepfakes. So this is a form of synthetic data generation. And the goal here is to replace the face of one individual, of let's say person A, in a video with the face of a person B. And this is basically a really trending topic right now. And one way to do this is to first build. So we start with some databases of only face images. We have a lot of faces of A and a lot of faces of B. And we built an encoder that encodes these pictures. And to decode them, we use a different decoder for A and a different decoder for B. And the objective, again, is to reconstruct the face of each one as best as. So the system, what it does at runtime, we have this video and we process it on a frame-by-frame basis. We use phase detection to extract the crop. We extract the face and we pass it through the encoder. And the main thing here is that instead of passing it through the decoder of the same person, we pass it through the decoder of the other person. As a result, we reconstruct the face with the features of the other person. Now, there's also other details that go into this, like, for example, having a face mask or some landmarks and alignment. But this is the gist of the idea. Now, for this to work, a lot depends on the lighting, of the expression of the people, the pose, and so on. And as you can see in the figure on the top, this does not always work. But this is a very active area of research, especially if we want to detect this kind of manipulations in videos. So there is a lot of challenges that are happening with just this this target. So these were some of the applications of GANs, and you can find many more, ranging from video games that use GAN to increase the resolution of images, from astronomy to chemistry, and basically, I believe even in music. It's quite a popular technique now in many fields. So the main idea of GANs, just to summarize here, is that they use this adversarial setting for training a generator and a discriminator, and they take basically deep learning way beyond traditional pattern recognition. And it's one of the true revolutionary ideas in the past few years. So we've seen both an autoencoder, a variational autoencoder, and GANs, and this gave you an idea of how to use deep learning for generative modeling. And we can see that in many ways, these GANs are the inverse of the autoencoders, in that they have the data space on the inside, and variational autoencoders have it on the outside. So GANs are explicitly set up to optimize the generation task, whereas the variational autoencoders are all about learning latent representations. So having said that, the idea of adversarial training can also be transferred to variational autoencoders. So you can find a mixture of the two. Now, in general, for images, you can see that we can observe that the images generated by a GAN are much sharper, and in general, GANs provide a higher variability in the kind of faces or objects that they can generate, whereas a variational autoencoder are usually a bit more blurry, and they offer lower diversity than GANs. But of course, there is a lot of effort in training GANs, and you need a lot of expertise to be able to train GANs rather without any trouble. Now, on the last part of this lecture, I want to talk a bit about a generation task, but a different type of a generation task. So we've seen that in previous lectures that usually the setting is that we want to use neural networks to classify images. So if we give them some digits, the network comes up with the answer with some probability. Now, the question is, what if we could generate an image that looks almost identical to these images, for example, to these digits, but we generate it in such a way as it would cause the network to intentionally misclassify these digits? Okay, so for example, we could have these two images that contain the same number, but the way that we generate them, the network misclassifies them. And you may be surprised to find that adding some imperceivable perturbations to the image, some noise, can cause drastically different model performance. So in the example here, this is a very famous image. We add some noise to a panda, and then this is classified as a gibbon. But for us, if you look at the image, it's clearly a panda. So even if research is constantly pushing machine learning models to be faster, more accurate, and more efficient, this idea, these types of samples show that there's a lot of work that needs to be done with respect to the robustness of the model and how we make sure that the models operate securely. So we'll briefly talk now about this idea of adversarial examples. So when we talk about adversarial examples, we are referring to samples that are designed to intentionally cause a machine learning model, in our case, a deep learning model, to make a wrong prediction. And adversarial examples are important because they can cause a system to misbehave in a way that it could be really dangerous. So if you, for example, have an autonomous vehicle and you somehow manipulate one of the traffic signs in a way that will fool the machine learning model, then that car can crash and potentially lives could be lost. So this is a very active area of research, and it's now called, you can also find it in under the name robust machine learning. And it's this idea of first identifying why these patterns exist, why these examples exist, and how to mitigate their effect. Now, there are many categories of adversarial attacks, but in general, the goal is to add the least amount of noise so that it's imperceivable, that will cause some sort of misclassification. And there are many categories of attacks. So depending on what we assume that the attacker knows about the model, so attack, basically the model has access to everything and can manipulate the model to find these examples. Or we could have a black box attack where the attacker only has access to input and output of the model and tries to infer what the model does based on this relation. There's also different types of attacks. So we could have just a misclassification attack where the model we just want to change the input, so the model just makes a wrong prediction. But we could also be a bit more specific and say, okay, we want to make a prediction that the image is of this particular class label. So one of the first and perhaps most popular attack is the what is called the fast gradient sign method. This is a white box attack with the goal of causing a misclassification to the neural network. And the main idea is that it leverages gradients from the neural network in the same way that we use the gradients during training to alter the input image so as to cause a change in the classification prediction. So the idea is that we apply backpropagation as normal, and when we reach the input layer, instead of getting the gradient with respect to the weight of the weights of the first layer, we take that gradient with respect to the input, and we add this along the chain of the backpropagation that we have generated. And these gradients can then be used to manipulate the input image. So instead of subtracting the gradient, as in a normal training, we add the gradients. So because we want to cause the loss function to increase, we want to move in a direction that will cause the loss function to go up rather than minimize it. And we do this in a process by going through epochs, like in normal training. And here is the formula, basically, that is used to change the input. So we have the x prime is the new input, and we have the x, which is the input image, and we add to it the sign of the gradient multiplied by some small value, which is called the epsilon. And for this, we first need to find the gradient of the loss function with respect to the input. And we'll see the effect of this epsilon a bit later on. And overall, this process, what it does is to move to the gradient direction that maximizes the loss, so it could cause a misclassification. So let's see a more illustrative example. Here we have the x, which is the input, and we have the y, which is the label, the ground truth label, and theta are the model parameters, and j is the loss function that is used to also train the network. So the input image is initially classified correctly as panda with some confidence. And during the attack, we backpropagate the gradient with respect back to the input to calculate the gradient with respect to the input. Then we take the sign of that gradient and we multiply it with this small epsilon value, and we add it back to the input image. So at pixel-wise, we find the direction that we have to change each single pixel. And when we put it back to the network, this will cause the network to misclassify this image as a gibbon. But as you can see, this is clearly still a panda to us when we look at this image. This is indeed a very intriguing phenomena, how the networks can be so easily fooled. And the application of the attack, the way that we update is quite similar to how we apply the weight update. But in this case, we just take the gradient with respect to the input. So if you break this partial derivative using the chain rule, you will understand basically that it's the same flow, but we just add the component with respect to the last component with respect to the input. So we also talked a bit about this epsilon value that controls how much change we can add to the image. So this step value epsilon plays a role in the trade-off between how much do we degrade the accuracy and how much we change the visual appearance of the image. So this is a trade-off that the attacker has to consider. If we change it too much, then it could be perceived, and a human can flag as a wrong input. Otherwise, it might not make much of a difference. But it's nice to see the effect here on the NIST dataset digits. So for small values, we can see that we still cause the network to mispredict. But as we increase that epsilon, the noise gets really visible. But it's interesting that even in these cases, humans can clearly see the digit. Now, another common method of fooling deep learning models is using what is called an adversarial patch. So this is a physical patch that we can place on top of an image or on a real surface that is monitored by a camera, and it causes the classifier again to do a wrong prediction. And the way we generate this image is that we basically need to optimize it across different background images, different positions, different scales, and so on. This will it's necessary so that the patch works in many situations. So in the end, you can print out this image, and you can deceive many classifiers if you place it in front of a camera that uses a similar model. Now, we've seen many examples of how can we fool a deep learning model, but the main question is why is it that deep learning is fooled so easily while a human can clearly see those images and see that they belong to the same object or same class? This implies that these models do not actually learn meaningful features that define the object, but probably they may find the easiest way to classify an image, even if it causes it to misbehave with small changes. So it might not be based on deep understanding of what the object is or what is the underlying task, but rather the easiest association they can make with specific pixel patterns. Now, deep learning models form a complex relationship between the image and the output. However, there are components, the main components they use. So, for example, the convolution operation, the ReLU, these are increasingly linear. And this is this linear nature, this linear compositionality of networks is what basically allows for these adversarial examples to be so prominent. So this ease of optimization, this way of being able to train big models came at a cost that these models, because of their linear nature, they can be easily fooled. Another important thing is that adversarial examples are not a feature of deep learning, nor are they only possible for images. So you can also find adversarial examples for different classifiers like SVMs or linear classifiers, as we have here. And we can also use it with different data types, like, for example, audio. What we see here is that we are able to break really easily a simple linear classifier. So by adding these types of this noise to the cat image, it causes the classifier to predict the class as a bus, which clearly isn't. So it seems that it's not a problem of deep learning itself, but rather the fact that we use linear components that make the model increasingly linear that causes this behavior. Now we see some more examples here of adversarial attacks. So on the left, you see some images where on the left column we have the real image, and when we add these specific noise patterns, all the predictions are all these images are predicted as ostrich, which clearly it isn't. Another intriguing aspect is that these attacks can also surface in printed images. So we can get an image. This is the example on the right. So we can get an image, we can add some adversarial noise, we can print that, and the effect of the adversary will still happen through the printed image. So if we have a smartphone that runs the classifier, the image that the phone gets, if we process it with the classifier, it's going to have a same effect. So in this case here, a washer is misclassified as a safe, which clearly it isn't again. And one final note is that the examples we showed are more geared towards classification, but we can have the same effect, the same impact with different types of vision tasks. So, for example, you can train a model to adversarial model so that you can find the patch that when you print it and you hold it, a person detector will not be able to detect you, so you can hide from surveillance cameras. You can also modify images to full segmentation models that are applied on autonomous vehicles, for example. So autonomous vehicles need to use semantic prediction, dense prediction, so they can, for example, find the drivable area that they can move into. Now, if you take that image and you distort it through an adversarial attack, you can cause the road to disappear, which will make the vehicle either stop or turn in a way that you don't want it and cause accidents. So these are research-driven efforts, but they can have a very meaningful impact. So I remember I saw a video of there was an autonomous car driving, and they put some specific patterns on the road that caused the car to go around and around in a circle. And because they caused the networks running on the car to see lines, that caused it to steer. Whereas if you look at the road, you wouldn't see any line. It was just some small patches here and there. So these things are really affecting real systems that we use in the world. So we need a way to deal with adversarial examples, but it is difficult and is more related to the cybersecurity aspect of it. Usually, this is a game of a cat and a mouse. So between attackers and defenders. So once we find a solution to something, the attackers can find a way around it, and then we need to find a new solution. Now, nevertheless, there are many defenses that people started to look at. Perhaps the most common would be to generate adversarial examples and include them in the training set. So the classifier learns to adapt its behavior based on these patterns. Some other ideas include adding non-differentiable transformations, so that these types of transformations, they block the back propagation, so there will be no signal for the attacker to calculate. But there's still a lot of research in these areas. There's no one defense that is able to deal with all different attacks, especially if they adapt. But it's a very important research area. Finally, one final note is that we could generate adversarial attacks for example, the VGG model, and those same attacks will translate to a different model, like a ResNet, for example. So these adds another dimension to the adversarial attacks, that they are transferable between convolutional network architectures. So in conclusion, today we saw a different perspective of deep learning models beyond the more traditional pattern recognition perspective. We have seen how to use them so that they provide us with an indication of training data bias and how to generate new samples. With respect to the generative adversarial networks, we saw that they provide a very powerful framework that we can use to improve the capabilities of image generation and image-to-image translation tasks. And finally, we also touched a bit on this big problem of adversarial attacks that can also affect deep learning models, and they can degrade the performance of the classifiers.